John, would you like to start?
Yes, okay,
Thank
thanks.
you so much.
So at Wolfram, what we do is we make a mathematical programming language called the Wolfram Language, and we're known for instantiations of that, like the Wolfram Alpha knowledge engine you can use on the web to answer knowledge queries, the Mathematica application that's used in a lot of universities for doing research. And amongst other things, I lead the technical services team in Europe where we use our technology to try and solve problems, do data science, do modeling projects for outside customers. So that's the background, the perspective I come from, where we're trying to do all kinds of maths, all kinds of modeling in one place and bring it all together. And so from that perspective, I wanted to give a bit of a tour of mathematical modeling. I'm going to try and keep it very light, and all my examples are kind of mostly pretty toy examples. But I'm going to start, at fear of being patronizing, right at the basics, and then we'll work up towards machine learning by the end of the hour. So let's start as basic as we can. What is a model? Because I think, in the wider public, this is quite a misunderstood thing of, all it is, and I want to de-hype most of these things, is it's just a representation of something else usually in the real world, not necessarily, but a representation of something else that has some rules of behavior that are useful in predicting something about the original thing. So just like a physical model, like an aeroplane in a model aeroplane in a wind tunnel, it might tell you something about what the real thing does and how that behaves without you having to do the real thing. And that's all we're doing. So let's start with the very simplest, the one I could think of. Some data from various trips from, fake data of how far I am from home after 8 o'clock in the morning on a bunch of days. Now, we can do the drive and find out how far away I am at any given time in order to find out. But if we want to make predictions without having to physically get in the car, what can we do with this data? Well, the first thing is the data, which actually is a model that we can, I can't quite see that, made the font's too small here, but at half an hour, I'm at 12 miles away, according to this. That is a representation that we could use to look up. But if we want to make wider predictions, then we want a kind of slightly richer model. And the typical thing to do there is to come up with a model. And it looks a bit like a straight line. So we'll have a straight line. And the straight line is a model. Now, there are different straight lines we could make. We could play around with this. And there's some automation which I can use to click on automatic to find the best, and we'll talk about what best means a little bit later, model. Now we can make predictions on things we haven't seen. Where am I likely to be after this length of time? Where am I likely to be after that or before the data started being collected? So that's the prediction. It's nothing very deep, but there's a model. So what can we do with that? We can interpolate unseen values with that model. We can extrapolate. Very often with models, you can discover some other properties. So for example, not immediately obvious, the steepness of that line, that tells us on average how fast I traveled in this case. So that's another property that we can get from this model by kind of going backwards from the model. But it's important to understand, and this gets less obvious as the models get more complex, it doesn't tell us anything about how the system works. We don't know if I'm flying or driving or running very fast. We don't know anything about how the data was collected. None of that is encapsulated in the model. It's totally abstracted away from the real world. And there's a lot of things about the real world it just simply has no hope of telling us. And the last thing is, it's not AI. And later it'll start looking like AI, but right now, this is not the computer understanding my journey. It understands nothing. It's a straight line, and I can put a number in and I can get a number out. And that might be an amazing prediction tomorrow when you say, where is he? Let's have a look on the graph and look on the satellite and see that's exactly where I am. But that's not some insight of intelligence of the computer, that's just the model doing what the model does. So what's in a model? And I'm going to abstract a little bit away here, but let's take this one as the example. There's 3 things that we have in a model, which we have to get from somewhere. There is some kind of structure, some kind of innate shape of the model. And in this case, it's the equation of a straight line. Now, why is it a straight line? I picked a straight line. So that came from me, that I chose AX plus B as a mathematical model. Then it's got some parameters. In this case, I guess if we go back and see what we had here, I got those numbers wrong. Actually, the parameters in this case are 20, nearly 20 and 1.5. I think I wrote this and then changed my mind about the model. So the parameters here are about 20 and 0.5. So they're the adjustable bits The shape doesn't change, it's always going to be a straight line, but we can adjust the A and the B to change which version of the model. And again, we could choose those. I might know a priori that I'm going to be traveling at 20 miles an hour, or whatever this parameter A represents, and I might insert that, or I might do what I did when I clicked this, this automatic button, which is to figure that out by looking at the data. So by snapping the lines of the data, we've acquired this parameter from the data, and that is, at its simplest, machine learning, because the machine, through some mechanism, learned the parameter value for A that we needed to make this the best model. And in this case, the rules of behavior are arithmetic. We multiply, we add, and all the things you can do with a polynomial, like take the derivative of the line or the area under the curve. All of those things we can do to it, but it's the maths rules in this case are the rules of behavior. Now, those three things are infinitely variable, and I want to give a kind of tour of some of the different choices that we could have made for that or other models. So I've tried to group them, not in a very precise definition, but the first collection I'm going to call functional models, in that I've got a mathematical function like ax plus b that is the structure of my model. So that could be other versions of that algebra, but they could be functional things like functions like sine and cos, or other sort of mathematical representations. There's also sort of more implied versions. So here I'm going to get into a slightly more difficult example here. This is a classic chemistry kinematics problem where chemical A is being turned into chemical B. B reacts with itself and makes C and B, and C also reacts with B to make back into A plus C. So things are going round and round in a circle according to some rates. Now, if we look in the kind of theory for how this works, then you can describe these in differential equations. The rate of change of A is those rate constants times the concentrations of the chemicals. And we end up with a system of equations, but these are all basically just a complicated version of what we did before, which is we've got equations describing the physics of the situation. And then we can ask it to, let's say yes to that. We can ask it to solve that and figure out the concentrations over time. And you can see sort of some exotic behavior appearing where the concentration of B goes up quite steeply, flattens out for a while, and then all gets used up and there's none of it left at the end of the reaction. And so these kind of features now are the predictions we're starting to get out, the concentrations of each thing over time, and the rates of change and so on. Now, it turns out things to do with rates of change come up a lot and get progressively more and more complicated as you have the rate of change of things, systems of rates of change, mixing rates of change with ordinary equations, rates of change of things of more than one variable, and they get, there's a whole science of just doing those. Here's a slightly more complicated example, but it's fundamentally the same thing. I've got, instead of an interval of time, I've got an object this time. And even this, of course, this here is a model. So it's not a real spoon. It is, in this case, we've got a kind of mesh representation of that made out of little triangles and points that are joined up as an approximation for the spoon. And we've got some kind of knowledge of the fact that it's made out of silver. And one of the things we've been doing at Wolfram is to try and allow you to describe the very complicated things like stress and strains and fluid flow in higher level language terms. So we've got this language that says a solid mechanics component with a solid boundary with a load on it at some position, and a bit of the spoon which is fixed. So I've got some area which is bounded by this clamped and some loads. Basically, I'm sticking this in a clamp and putting a weight in the spoon. And I should have run this because it takes a few seconds. In the end, the modeling is done just as a lot of arithmetic, because the way most of these differential equation solvers work is they break into little bits and they say, well, if the force on this bit with a bit next to it is this, let's do that, and then repeat with the next bit, and repeat with the next bit, and do many, many little calculations. And hopefully in a few seconds, we will calculate what the spoon would look like in an exaggerated form after the load has been put on it. So here is the original, and it's being lowered down, and I can't remember whether the coloring is displacement or stress. But in all these cases, we've got a kind of mathematical description of the situation. Now, there's a whole bunch of models that are not, in one form or another, deterministic. They're either not deterministic because we can't work it out And so we have to do random experiments to try and figure out what happens. Or they're not deterministic because the things we're putting in, we don't know what they are. If we don't know what time my journey will set off on that drive, then the straight line model can't work because you don't know what number you're putting in to know what number you're getting out. So there's a whole world of models based around probability. Now, one way of doing that is in a very equational way, is to describe probability distributions instead of numbers. So where we had that straight line, we put a number in, and we got a number out. Well, we could put in something that is a distribution, a kind of range of values and their likelihoods, and then get either some number out or some other property out. So let me show an example. This is some data here of wait times versus durations for the old faithful geyser in Yellowstone Park. And you can see that generally, if you wait a bit longer, you get a bigger eruption that lasts for a bit longer. But these aren't inputs and outputs. You don't kind of choose to wait a length of time in order to get a bigger eruption. They're just correlations. So if we wanted to know something about how long we might want to wait, well, we just got a whole bunch of numbers that are random as far as there's some physics, but we have no model for the physics. I don't know what's going on under the ground, so I can't build equations for how the steam gets through the cracks. So I'm just going to get that waiting data and make a plot of just the wait times. And putting them into bins, we get a sense now that there's kind of a lot of the time you don't wait very long. But if you don't see it after about 60 minutes, you'll probably wait until more like 80 minutes before you see it. And then there's a whole bunch more. Now, at this point, I'm going to choose a model. And again, this is coming from me at this point. Well, the histogram is a model. We could just work with that. But that's introduced weird artifacts here that we know this is continuous time. That it's not like if the eruption doesn't happen after 60 seconds, it won't happen until exactly 2 minutes. These aren't squares. That just happens to be the way to count the data up. So I can describe things in terms of these probability distributions. So gamma distribution is a bit like a normal bell curve, but it comes up a lot in waiting times. And I'm guessing here, just by looking at the picture, that there's going to be two different distributions. We don't know where they're centered or how wide they are, and they're mixed together in some proportions I don't know what they are. Now, that thing itself is kind of like an equation. It's a probability distribution, but it's a symbolic expression that describes my assumptions about the way I think it'll behave. And then just like we could fit the line in the straight line, we could figure out what these parameters are by going back to the data. And we can say, look at the data and guess the numbers. So here's the numbers that it's learned. And if we look at that with the original, we'll see now we've got a model which is smooth and does seem to describe the data. And that's now something that we can work with. It's a thing that we can ask predictive questions of. So we could take that new distribution we just built, and we can ask, does it fit the data? If we get a small number here, we should reject it, because I might have picked a model that simply can't fit the data. If I said, oh, it's obviously one square wave, well, it isn't. That would fit very poorly. But it's saying here, this is plausible. This is a pretty good fit. The closer to 1, the better. The closer to 0, the more likely we want to reject the idea. We can ask the probability of how likely am I to wait more than 80 minutes, given that that wait time is coming from my new distribution, and there's 32%. And once we've got this kind of language, we can ask really exotic questions, because we've got this ability to describe behaviors of distributions in terms of distributions. So here I'm asking a much more complicated question, which is, if I took 3 visits and put them in order and pick the third one, what's the longest I would have to wait on 3 visits? What's the probability that that's more than 80 minutes? Then that's 68% chance that the worst visit out of 3, maybe I'm a tour guide and I want to, I'll have you walk past here 3 times during the course of our day, and I want to make sure you're going to see something. How long do I need to wait to make sure it's at least 50-50, for example? Or we could actually just do experiments and just make data to throw into some other model. Now, this idea of making data goes to the other end of probability-driven models, which is sometimes it's not really about the model, it's about the fact you can't really work anything out for sure. We just haven't invented the maths for it. And a lot of those problems can be solved with something called Monte Carlo methods. And the idea is, if you want to know how often you'd win at roulette, It may be impossible to work it out, but if you play 1,000 times, now you know how often you'll win. And so it's the same thing with the maths. So new scenario. This is genuine air transport data from the US. Actually, let's just get that on screen. So this was through the 1950s and 60s, the number of airline passengers there were, and you can see it's got a general trend and a general seasonality, and there's probably some randomness in there as well. As you get into the probability world, there's always one more thing you can think of that's more complicated. So in my Old Faithful example, there's an unknown that happens. It's an event, and it happens, and it lives in isolation. In a time series, there's a random thing that might happen. It might be busy today, or it might be less busy, but it's not in isolation. If it was busy yesterday, you're more likely to be busier today. So, because we have things like a trend. So in a time series model, this is the kind of complicated representation of the best fit, kind of like my curve was before, but I can't even make a picture out of this one. Something called a seasonally adjusted arithmetic mean, I can't remember what the R stands for, that it's picked, is its best representation that then allows me to predict from it. So the orange is now the future prediction. But very often you don't just want the future predictions on things, you want to know what's the worst that can happen, what's the best that can happen. And while the core prediction was straightforward, actually working out those best and worst and what's the worst that would happen if I'm in 1% of cases? What do I need to engineer for? There's no maths really to calculate that. So the way we deal with that is we just try it many times. So random function is a way of saying, play it out, throw the dice. And I've asked it to throw the dice 50 times. And now we've got 50 different simulations. And you can see one of them's gone way off down. Some have gone way up, some are a bit flat. We could do that 10,000 times, but I wanted it to be few enough that we can see the lines here. And now we can say, okay, for 1966, what's the range of values that come out? And we can take that out. What's that? That's the distribution. That's what we just saw a moment ago. It's a different kind of distribution. And all those things I could do with the distribution now, like plot the cumulative risk, that's all available. So these things start to kind of join up, that you've got what's called a stochastic differential equation here, generating something that's a distribution that we might fit a curve to using algebra. And while these things are very different worlds, conceptually, the mechanics all end up joining up. I'm not going to show one here, but just give a sense of how, when you think you've got the ideas, there's always more. There's the world of spatial statistics, where instead of what happens next affecting the probabilities, it's where you are affects it. So a good example would be trees. Trees are more likely to be close to each other because the acorn falls off and grows a new tree, but they're not very close to each other because they're in the shade. So you end up with attraction and repulsion, and you end up with clusters called forests. And so there's a whole world of modeling things where you don't know what's happening because it's luck, but you do know something about the relationships in space. So we've got kind of isolated unknowns, time-related unknowns, and space-related unknowns, and I'm sure there are others as well. Right, another whole class of modeling is rule-based. And one of the earliest of these was The Game of Life by Conway. And the idea of The Game of Life is that he hypothesized that a simple kind of bacteria or moss or something might starve if it was surrounded by, so if the black represents the presence of the lichen, say, and if the blob in the middle is surrounded by lichen, it'll starve and it'll die out. If it's empty and surrounded by lichen, it's not going to start again because it's still starved. Whereas if there's nothing there at all, there'll be no lichen because nothing can start it. And if it's on its own, it kind of doesn't have enough life support, it'll die out. But there are cases where if there's a modest amount around the point, it will survive. And if there's a hole in the middle of a slightly colonized area, it'll spontaneously appear. And then you can draw a grid and put some dots on it. And then every time you tick the clock, you apply these rules. So you look at the 9 points and decide which of the rules they match to, and then you apply the rule. And it turns out, as is generally true of these kind of rule-based behaviors, is that very simple sets of rules, in this case, what are there? There's about 18 rules, describe really exotic behavior. So you end up with, the migration of different colonies dying out, colonies becoming static. And in fact, you can engineer these kind of particles to make simulations of a computer out of bits moving around, or simulations of physics particles colliding and turning into new particles, all out of simple rules that are just applying repeatedly. And in fact, my boss, I actually claim to have read his book, New Kind of Science. It's 1,500 pages long. I got to page 30, but I've heard him talk on it a lot. It turns out that that very quickly, in very simple systems, you get exotic complex behavior as soon as you get feedback systems of rules. So he studied the simplest set, which is a 3-bit rule, where so there are just 8 possible bits to scenarios to look at. So 256 possible programs, and it turns out of them, some are just die out to white immediately, but out of the 256, about 30 exhibit behavior that is so complex that it cannot be reduced to anything simpler. So you can build a simulation of the universe out of one of these 3-bit rules if you just ran it enough times. And while I'm not going to go there, his multi-physics project is trying to apply those ideas on a high-dimensional graph with simultaneous computations going on. So he's made it a bit more exotic, but he's hunting for the fundamental theory of physics. He's got a big ego, so he thinks he can do it. Now, this was the very first, and this is as simple a rule as you can get, because we've got a grid and we just got this, does it match a pattern, move on. But what this actually is a simple example of something called agent-based modeling or agent-based simulation. And so here's one I wrote, which I did at the beginning of COVID. And I wanted to think about the question that Boris at the time was putting out, that we don't want to lock down too soon, because people will get bored of the lockdown, and then the sooner you lock down, the sooner they'll start breaking lockdown and start wandering around again, and therefore we should wait until the right moment to lock down. And I wondered whether that was true. So I'm going to skip through the code here because there's too much to explain in detail, but the basic idea here is that I can build a population of agents. So that there I've highlighted as an agent. So an agent is just a blob of data that represents all the useful properties of, in this case, a person. So I gave them a status. Are they infected or not? I think I chose vulnerable if we didn't have vaccines when I wrote this. This was very early days. They were either vulnerable, they were infected, or they were immune because they'd recovered. They didn't know then we could reinfect. They've got a place in space, and they're just going to wander around space randomly. They've got a direction of travel to track which direction they're walking. And then I've got my isolation, which is how long until they lock down. So this person will never lock down. This one will lock down in 5 time steps. And then the idea is you write a bunch of rules. So some of them are just the physics of the situation. I say the position, each time the clock ticks, the position of each agent will be updated so that if they're in isolation mode, then it's just the current position. Otherwise, we'll take the current position and add some little step in the right direction. And the status is if something like if they touch somebody who, if they're vulnerable and they touch somebody who's infected, they instantly get infected. So very simple rules. It's not trying to be realistic, because to try and be realistic, you have to map out so many different things that I can't possibly know. So I was trying to test a simple hypothesis. I kept it very simple. So basically, you just keep running the system, updating each of those agents, and then running the system again. I'll skip to the end here so you can get a sense of what happens when you run the system. Is I allowed it to set some rates of the initial disease. So 1, here's our diseased person waiting to go. The patience of how long they'll stay isolated. The isolation rate, which is when you say lockdown, how many will actually obey. And the delay before we start. And then when you run the simulation, you can see them wandering around. Every time the red blob touches somebody, they become infected. There's the lockdown kicking in. Some of the people are now starting to break the lockdown and starting to wander off. And some of the infected are visiting people who are locked down as well. And on the right, we're tracking the status at each time step. So the red is the infected, and the green is now the people who are starting to come out the other side. And of course, there's 18 people in total, so that never goes up or down. I didn't have anyone die in this simulation. And then eventually everyone comes out the other side. Now, it's fun to watch it, but actually you don't need to see the, I did that for fun. The thing to do is just to set it up so you can run different scenarios. And here are some of the different scenarios I ran for for different rates of isolation policies, and you can kind of see the effects of exponential growth, and then in this one, isolation kicks in and it slows down the growth. And I don't know quite why. I think this is the first batch is starting to all simultaneously get cured because they had a similar length of infection was slightly programmed. As it turns out, my conclusion was lockdown the sooner the better. And it seemed like Boris's line was just an excuse to why they need to get some things in place before they said lockdown. Right, so there's lots of different flavors of these things, but that sort of sets out some of the basic ideas of equations, probability, or what's called stochastic models that are based on randomness, and models that are based on programs that update in time steps. But a big part of the world is making models out of models. And in a way, we're always doing that, even when we think we're modeling using our human intelligence. And you know, maybe I decide I'm modeling something to do with pressure of a gas. I know the ideal gas law. Well, all I'm doing is plugging in some model that Boyle invented 200 years ago, which of course breaks down at super high pressure where gases turn to liquids, and probably breaks down at super low pressure. And so a lot of the time when we're doing physics and engineering, all we're doing is reusing models that other people have worked out and assuming them to be good enough to reuse. So one of the things we get involved in is to try and make that really industrial scale. And I need to find here some software I've got hiding in the background. So what you end up doing is you want to build models together in order to make a model. And then you can make models out of those models, and you can work higher and higher levels. So I'm actually going backwards here. Here is my model for a Segway, one of those little bikes you stand on that kind of balances upright. And at a simple conceptual level, all a Segway is an inverted pendulum, some gearing system with some wheels on it, a motor to drive it, and a controller to make some decisions. But if we drill down into the motor, you can see I've set that up as having, it's got an actual motor component, but it's got some electrical components like a voltage source and a resistor and an inductor and an earth. And if we go back up, we can go into the gear system and say, okay, that's got a horizontal translator and some kind of rotation to horizontal converter. And the pendulum's got a bit more going on in it. There's a joint and a damper, and there's an angle sensor which is going to be needed to feed back into the controller. And the idea is that we draw those things and wire them up like a circuit diagram. But what all we're doing there is taking things like, if I look at one of these things like a capacitor and go to, instead of a pictorial representation, so the font's a bit small here, but inside here, we've got the equations of behavior of a capacitor, which for capacitor is really simple. That's straight out of, I don't know if they do it in GCSEs, but certainly A-level electronics would cover that equation. So when we, I've closed it now, where was it? There we go. So when we start building up these models, all we're ever doing effectively is building collections of models, that equation for a capacitor, and the lines just represent the joining between the variable of one model and the variable of another. You've got to map the variables so that if they are wired together, they share the same thing. All the things that are on the same wire share the same voltage at that moment and things like that. And once we've done that, then we can start running simulations, which is to turn that picture into the full set of equations. So build experiment. Then fundamentally, it's differential equations like the one I showed you code for right at the beginning. And it has to build the solve for that, and then it has to run it. And then we get, here's what happens from the initial conditions I set up, which I think is giving it a bit of a poke, and it has a little wobble as it tries to sort itself out and ultimately stabilizes. So there's some world of models, but I've been glossing over a big divide in the way things have changed. And all of that's driven by, how do we choose the model? Why did I pick a straight line? Now, that was, at that point, a completely human-driven thing where I said it looks like a straight line, but I could easily have picked a curve, and maybe that would be slightly better. And very often we're driven by the idea of, yes, well, I know that there's a speed limit on that road, so the physics of that is a constant speed, and we have this sort of theory-driven approach. But there's lots of places where you don't have a theory, and what do you do then? you either have to kind of work out every aspect of the theory, and this is the problem that big simulations like global warming have, is can I think of the theory behind everything that might influence it and feed that in to get an accurate model? Or the more recent movement has been towards data-driven, which is to say, I don't know, let's just look at the data. Now, the idea of kind of, is it true versus does it work, is a really kind of philosophical point here, that the kind of hardcore physicists will say, but that's not true. You can't model that with that equation, because I know that the real thing's more complicated. But if we go back to Box's famous quote, all models are wrong, some are useful. It doesn't matter if it's wrong. And it doesn't matter if, in fact, you have no theory at all, and you've just made up something that happens to fit the data that has nothing to do with reality, because the model never had anything to do with reality. The question was only, does it tell you something useful? Is it useful? Does it work? And so that sort of brings us into the rise of machine learning. And the idea of machine learning is basically to come up with some models that are very general. So the straight line, there's not much you can do with it. I can make it steeper or move it up or down, but it really can't be flexible. If I've got data that wiggles all over the place, it just isn't flexible enough. It doesn't have enough freedom to be able to fit to the data. So we come up with models that are much more general, that can be forced into any shape we want. And then we drive that shape entirely by the data that we've seen. So let me show you what that looks like in practice. And in Wolfram Language, we try to automate this out of sight. So I'm going to take some data here, which is, and I should probably show some examples of it, some wine training data. Can I just get it on screen here to give you a picture? This is a classic machine learning toy data set, which is a collection of wines that have been measured for some properties like acidity, but they've been rated by a human to be what their quality is. I think it's from about 2 or 3 to about 9. So here's a wine that was very good, and here's the properties that were measured in it. What we're doing with this predict function is to just say, here's a collection of about a dozen standard machine learning models. Use one of them, figure out which one works best, fit the data to it, and it's decided on its own. It's going to pick random forest. And let's see if I can remember. Random forest, it's going to pick one I don't know so well, is I think a kind of tree structure where it's building different ways of slicing the data recursively. And it does that many times, and then picks the ones that seem to have split the data into the 10 bins best, if I'm remembering that correctly. And then we can give it the unseen examples. So here's one I took from the data set. It has a true value of 3, and we'll see what it comes up with. 4.6. Well, on a 2 to 9 scale, that's not terribly far off, but it's not done such a good job here. But the point is that I haven't got involved in that at all. I've just trusted to do this. Now, I could do something a bit more manual here and say method goes to, I know, let's do the k nearest neighbor method and see what that does with it, and that's got worse. So its automated choice seems to have done a good job. But the point is, even this, I'm still not deciding all of the subparameters that say what kind of size of neighbor. All of those things are coming from the data. How big the clumps of neighbors together are, how you choose if you've got 5 neighbors that are 9s and 3 are 2s. Does that mean you should pick 9, or should you pick something between 9 and 2? And this sort of hunting method, you can see briefly the graph there as it's getting better and better prediction is, we'll go back to its choice. Oh no, this time it's decided gradient boosted trees. Oh, I'm resampling the data every time. So it's a different problem. So maybe that's why it's picked a different method this time. So, to the pure physicist engineer type, in a way that's kind of scary, because how do I know if it's right? And, how do I know if it's in any way true? Am I supposed to trust this black box? Well, to go back to what I said the real choice was, the question here is, does it work? That's the only thing that matters when you're in the machine learning world, not why or how. And you can check whether it gives the right answers, is the basic idea. You send the basic method is that you should always hold back some of your data, and then you apply it to that data and see if it gives the right answer. And if it does, it's doing something useful. There's an elephant in the room, though, which I'm going to address now, which is there's more than just does it describe the data well. That's a requisite. If it can't describe the data that you've got, then it's obviously doing a bad job. But what we want it to do is to generalize. And by that, I mean, we need it to find some inner essence of the truth of the situation. So if we go back to our first toy example, this line, as far as I can see, doesn't hit a single data point. But we're kind of cool with that because we've intuitively said, well, there's some errors here, but that's noise, that's randomness. Now, of course, in the real world, it's not random at all. It's a traffic light. It's some slow tractor in front of me. It's trying to get down St. Giles to park when I come here. It's things like that. They have, but I just don't know anything about them. So to me, they look random. Now, if I change the model and make something a bit more flexible, let's go to a quadratic. The curve has managed to make a better fit. So surely it's a better model. And we can do that some more. We can give it more freedom and it gets better and better at fitting. But if I take that too far, at some point, some crazy stuff starts happening. And at this point, in one sense, it's a better model because now it's going through every single point. It's 100% prediction on the data that I trained it on. But as a generalization, it's clearly doing crazy stuff here, unless it's somehow inferred from that randomness that there's like the international date line is here or something, and some crazy or some black hole, and I'm going to, some weird stuff's going to happen. Basically, this is overfitting. On the surface, in terms of our measure, it's better, but in practice, it's worse. And even on kind of like modest things here we've got a model that looks really good for interpolation, but for extrapolation, once we go outside the known area, it's actually got worse. Now, that's not a new problem. In classical modeling, the Occam's razor was really the guide here, which is simple models are good. And so when you were doing classic statistical modeling, there's all kinds of tests to say how much better did a fit get for the amount of extra freedom I had to give it. If I gave it 3 extra terms and I got a little bit better, but 2 extra terms actually got most of the way, then maybe that 3rd term is pointless. And we should not add extra descriptors that don't contribute significantly to the fitting. That's kind of fine still when you're in the loop as a human. But when you're abdicating responsibilities entirely to machine learning, then we need better techniques. And part of the rise of machine learning is methods that are more robust to overfitting in the first place. So this idea of fitting polynomials is terrible because polynomials just they always get more volatile as the order goes up, and so as you increase the quality of the match, the quality of the generalization pretty much goes down. But some of these other things like the gradient boosted trees and the nearest neighbor method are innately a bit more robust to overfitting. They generally generalize much better, but there are also a whole slew of modern techniques like validation sets where you hold back a 3rd part of the data, and as it's learning, the machine is looking occasionally at the extra set of data and asking itself, do I seem to be predicting that well? Oh, no, that's actually got worse, even though my fit's got better. Maybe my fit, I should wind back the fit and I've gone too far now and fix it. And one I added on here, just because I find it such a crazy method that works, is something called dropout layers, which is particularly in neural net modeling, you have a layer whose job is to go mad and forget. So it's kind of like having some kind of electrode in your brain that zaps you while you're learning and just resets things every so often. And randomly, as it's learning, it just decides to ignore part of the model. And the next time when it updates, it decides to ignore some other parts of the model. But the effect is it teaches it not to rely too much on any one bit of the model. So if, in fact, on that fit, the x to the 20 term started to become too dominant, and every time it drops it, everything goes wrong, it starts learning that's not a very good part of the model to put its faith in, and it starts spreading its decision over other features that it's looking at within the data. So here's the basic approach to validation, and I'm going to do a fresh example here. Another classic toy machine learning data set, passenger list of the Titanic. Here's the inputs. A first-class 29-year-old female survived, and there's 1,800 odd data points, I think. And I'm going to this time do classification. So it'll do a quick learn here, and it's decided, what's it decided on? Logistic regression is its method. And now I can ask it what would happen for me. Obviously, I traveled first class, and my outlook is not good. So the basic idea with the validation is you take the training data, which we've held back. Did I hold back? Yes, training data. oh, sorry, I'd taken the complement of the original data and the training data. So the training data was a random 900 set of passengers, and the rest of them, about, I don't know how many samples we got here, does it say? Actually, it's about 100 of that I've held back. It's using to test. So that's the key thing. Don't let it cheat by seeing things it's seen before. And this is a bit small, but I'll read out the numbers here. It's got number of test examples, 72, accuracy 65%. So 65 out of the percent of the 72 cases that it's never seen before, it made the correct prediction on, because it knows the truth. Because I have in the data set, well, it's gone now, but I know the true values of the ones that we haven't seen. So that is what's called ground truth, is compared. And 65 is not exactly self-driving car level of accuracy. And actually, it's not even enough to say that's better than 50-50, because died and survived. You think 50-50, I flip a coin. 65 sounds good. Actually, it's doing quite poorly here, because the baseline accuracy is 53%, because this particular sample, 53% had died. So actually, I could do better just by saying died, and I would have been right 53% of the time without using any intelligence, just by knowing which is the most likely. So we're comparing 65 to 53. Actually, that's a slightly skewed sample, because I think it's about a 70% death rate on the Titanic. So I got lucky with my test set. But let's go take a step back and readdress that what is does it work question. Because I kind of rather glibly said, does it work? That's all that matters. What does it even mean to work? What are we actually trying to optimize? So are we trying to optimize every possible input we could put in and be as accurate as possible over that? Or do we only care about inputs in a certain range? Are we only interpolating or extrapolating? And when we talk about the accuracy, where do we want it to be accurate? Do we want it to be evenly accurate? Do we want to be more accurate in around a reference point? Do we want it to be accurate more often than it's not, as opposed to the average accuracy? And even with the fitting example, I won't go back to it now, but the classic thing that we're taught in school is you're trying to minimize actually, let's go back to it. What you're trying to minimize is the sum of the square of the errors. So for each things where we've missed, we add up that, we find that error, we square it as a lazy way of making it positive, and then we add that up over all the points. And as we move the line around, that total sum of errors goes up or down. Turns out that is best if the errors are uniformly distributed across the range. And of course, that's not true for some things. As as numbers get bigger, very often the errors get bigger. So they're not plus or minus. If I have to guess, somebody's net worth, it might be plus or minus £10,000 for somebody who lives in my street. It might be plus or minus £100 million for somebody who lives in wherever that expensive part of London is. How we choose to optimize that, what's called loss function, really affects the output. And in the end, we have to care about what we're trying to optimize there. And even on very sort of practical levels, even when we try and optimize it being right or wrong on decisions, what are we trying to optimize? Do we want to minimize the number of times we go wrong, maximize the number of times we're going to go right? Are there particular cases we don't care about? If I'm driving a self-drive car, I don't care about the error rate. I care about the error rate that smashes up the car and kills people. I don't care about the error rate where it doesn't quite park in the parking bay correctly. So not all failures are equal. So part of the validation is to think about the kinds of errors. So if we look at our Titanic example now, we can actually look at how it failed. And we can see that in the case of actually died, it did... I'm trying to read this into what we're getting here. There's a bit of asymmetry here that says a third of the people that it predicted had died actually survived, whereas less than a third of the people it predicted to die actually survived. So it was worse it had a more false positive rate on the died. Well, in this case, it doesn't really make much difference because, but there are lots of situations where there's uneven weighting. If it's a medical thing and I can give you a £5 pill and cure you of something that might kill you, you are going to be really cautious about it. Any chance I've got the disease, give me the pill. If it's something where there's a small chance you have something and you're going to go through 6 months of chemotherapy, well, maybe it's the other way around a little bit, and you want to be more certain about the diagnosis before you make a decision. And those decision points are all things that need studying as well. So there's a lot of work actually in the post-analysis even though now the model building is incredibly easy, you just point the machine and go. Now the analysis is in the how does it work, in what ways doesn't it work, and what are the pros and cons of the decision. So this is another way of looking at that, is that, as I said, I can make a perfect predictor for, I didn't say this, but I can make a perfect predictor for whether you have cancer, if all we care about is not having any false negatives. I'll just say, you've got cancer, done. I can't be wrong. I will not miss a single case. And likewise, I can have something that has no false positives by saying, you're fine, just go home. And we can make the decision about what comes out of the model. Anywhere along that, we could say, we're going to treat you if you get 50% on the test or 10% on the test. And what this ROC curve is doing is showing the false positive rate across those different choices. Ideally, we want to be in the corner here where there's no false positive, no false negatives. We definitely don't want to be on this line. That's the model hasn't worked. We're not learning anything at all. And we're trying to get in the corner. But there's still some range of choices here. Do I want to be lower down here and minimize the false positives? Or do I want to pick a decision point more up here? And this obviously seems like a good place where we're getting good rate of return if we want low false positives. And it's not really obvious where the best point to pick would be for a higher false positive acceptance rate, but somewhere around here probably. And the nearest to the corners we can get, but skewed according to our priorities. So while machine learning has made the work simpler of the modeling, it's actually just exposed the importance now of understanding all of those human decisions that have to be made around modeling that we kind of ignored before because we were so busy trying to do the model. And we also have to ask, and I could talk about this for hours, but I'll just hit it with 2 data points. What even is truth? I had a ground truth there, which was, did the person die or live on the Titanic? We had a record for most of those, apart from a few that it was unknown. But most of the things in the real world are not so absolutely true. So one of the things always to watch out for is, well, first of all, data must be representative of the task. So here's a classic thing in terms of bias is that, there's often pointed out by ethics lecturers is the typical AIs, if you ask them to predict the name of the CEO of a company, it's more likely to give a male name than a female name. Now, that's not wrong from a modeling point of view, but what's wrong is that we've been fuzzy about the question. Are we asking who should we hire who has the right skills to do the job? In which case, the bias of the data that came from the real world that didn't look at things that way should be prevented from coming through and giving a biased answer. Or are we asking for a prediction of what should I call the person who I'm about to send an email to, and I definitely have to have a name, so I have to get, give me a prediction, in which case it's the right thing because the world as is still does have more male CEOs than female. So we've got to be really clear about what we're trying to do. Are we trying to predict what has happened or what will happen or what should happen? And we might only have the same data for all 3 cases. So now we have to start thinking about how do we prepare the data in order to remove biases that we don't want. And bias is not bad. We want the data to be biased because otherwise it doesn't predict anything. It needs to know examples of people who are bad employees and good ones. In order to be biased against the bad employees, we want it to say, don't hire that person. We just want it to not hire that person for the reasons that we think it's doing it for, not because it learned on some previous sexist or racist HR person that we trained from their choices on. And subtly, more subtly in there, you always have to be aware of human influence creeping into the data, because even if the data seems factual, humans have a way of influencing it all the way through. So one of the problems is that we often have proxy measures. An example I often use that caused a lot of controversy was the Pennsylvania probation service, which tried to make a predictor of recidivism. Would you commit a crime when you were released, so they could figure out who to release and who would be a risk to release. And of course, they looked at the data and said it's data. These people were released and committed crimes. These people weren't. Let's train it on that. But of course, ending up back in prison is not committing a crime. It's a proxy for it. It's the best we might have, but it's not the same thing, because in order to go back to prison, you have to commit the crime, you have to get caught, you have to be prosecuted, and you have to be convicted. And 3 of those steps are involving other humans in the process. And if you accept that American police system is not the fairest in the world, then that becomes a problem. And you can get it the other way around. You might release some people who aren't going to reoffend, but they get accused of something they didn't do. So it works both ways, that the human judgments that go along the chain can change this pure factual data into something that actually is still influenced and subjective of human behavior. So very often with machine learning, we're predicting what humans would do, which is a great way of cutting costs and getting humans out of the loop and saving salaries, but it's not necessarily doing a better job than humans would do without really thinking about the data. How are we doing on time? I think we're good.
Yeah,
Right. So this is one I get a lot when I talk about machine learning, which is how does it work? Why does it work? How did it make its decision? And of course, the ethics people really worry about this. If I turn you down for a bank loan and you turn around and say, why? I don't want it to be for some protected reason. You know, I turned you down because of your race or your sex or your disability or some other thing that would be illegal to do that for. But one of the problems is you have to accept in the machine learning world that apart from the very simple model, you will not know how it made its decision. If you ever get anywhere close, you're probably fooling yourself because it's so complicated inside these modern models, you can't explain it. And in a way, that's not any worse than humans because, you know, when I say to the old-fashioned bank manager, why did you turn this person down for a loan? Well, they may not have personal insight. You know, they may say, well, it was because of their salary and the job that they do, but actually it's they couldn't quite admit to themselves it's because the person looked like their father that they never got along with, and that's why they turned them down. And even if they do recognize that, they'll probably lie to you and tell you a plausible reason. So it's no worse than humans. But I always think the way we think about humans is a good model for this, which is you just have to accept I don't know how you're thinking. All I can judge you on is your behaviors. So for explainability, what we need to do is look at the behaviors of the system. And there again, we've got data science do lots of analysis on the model. So again, more weight on the analysis of the model. We can take this example of wine, and I can't remember whether that's the same one I had before. This was a low quality wine. And I've asked it for an analysis on how it made its decision. Now, it's not saying how it made its decision. We can't know that. But what we can know is, what if I don't tell you about the fixed acidity? And what if I don't tell you about the citric acid in it? What will your prediction be then? What if I don't tell you about either of those? What if I go through all of the permutations of withholding information from you and ask you the question, what have we got? 1, 2, 3, 4, about 10 things, 10 to the, is it 10 factorial or 2 to the 10? Quite a lot of different ways you can ask the question. We can then measure which had the biggest influence. And here, this plot is supposed to give us a clue to that says, without knowing anything, this wine would be a 5.9. That's the average rate for the whole data set. The biggest effect was the free sulfur dioxide that brought it down to 5.4 on its own. The next biggest effect was the alcohol level and so on. And then these last things had no real effect. And actually this total sulfur dioxide level in it was a positive indicator that the wine was not quite as bad as it was looking up to that point. So now at least we get a sense of what's been the influential factors. And we can do that en masse. This is for the specific case. Doesn't mean the next wine, it'll be based on free sulfur dioxide. But in order to figure out what it is in general, we can repeat that process over the entire test set. It takes a bit of computation. So I'm looking at 585 wines here. And now we get a sense of the average that the biggest counter indicator is going to be the alcohol level. So that has, actually the thing that has the biggest influence for bad wines is free sulfur dioxide. There's a whole bunch of points here that have been made terrible based on that value. The alcohol level seems very important for, and the color tells us whether that's the only thing or whether there were also indicators. So alcohol is a strong indicator, but it's not the only one. When it's a bad wine because of poor alcohol, it's also a bad wine because of something else, is what the blue's telling us. Whereas if it's a good wine because of alcohol, then it's probably, that's enough to tell you. I don't know whether, this doesn't tell me whether high alcohol is better than low or whether there's some sweet spot in the middle, just that that's the influential factor. And again, there's a whole world of analysis to try and understand behaviors and models. Right, let's wind back to something I said earlier again. Choice for discovery. And so we can choose models, or we can choose to use machine learning. We can build models out of models that we've chosen from history. But it turns out we can go even deeper on that idea of discovery rather than choice. And this is what where the world of deep learning came from. And I'm going to switch into a different field here and talk for a minute about how machine learning tried to solve the problem of computer vision. And the idea was we had things like nearest neighbor models and the gradient boosted trees they used earlier. They've been around for quite a while. So the theory was if we can just give them the right signals to look at, then we could learn what this thing looks at, like by giving them some useful features of the image. So the world set about trying to figure out how can we find features of images. Let's grab an image here. Let's get a picture from my camera. There we go. And it turns out you can find all kinds of features in programmatic ways. So this is the only one I'm going to do at code level. If we take a block of 9 pixels, and you add up 1 times all the perimeter pixels, and subtract, that should have been an 8 times the middle pixel, then where the image is constant, we'll get 8 lots of 1 minus 1 lot of 8, we'll get 0, we'll get nothing. But where there's a change, like an edge, then we'll get a value, because the -8 won't quite cancel out with the rest as it crosses over the line. So this is a rudimentary edge detection. And these are the kind of features they thought, if we can pick out the edges of images and circles and lines and so on, and I guess we can do that as well. So this is a better version of edge detection than my rudimentary one. I can try and look for image lines. What am I missing here? A square bracket. So here's some lines. I should set the threshold a bit higher, but you can see it spotted some horizontal lines and my sleeve. So it's picked out some things that seem to have lines. I can look for corners in the image. And so there's a corner and there's a corner of the white area. So these were the features they started feeding in. And I made some progress to take an image, pull out key features, feed those into machine learning algorithms, and then it kind of stalled. And the progress was, can we figure out better filters that pick out more interesting features? And these got more and more complicated as they tried to pick out, can we spot rough texture with a filter? The breakthrough came when somebody said, well, rather than choosing these, what if we use machine learning to discover those? And maybe the machine learning methods applied to those can then figure out the best features that feed in, and we'll make the chain that joins up the learning the features and learning what to do with the features into one long chain. And that is what is meant by deep learning. So here is a neural network that is in the Wolfram language. Now, this is now a much more complicated model. There's 20 odd layers, but actually, if you look at some of these layers, like this is a graph layer, there's 17 layers hidden in that. So that's just one of those layers. And it's made of these different components, and information is flowing through this network, and each step something is being done. Now, the something in most cases is really simple. Some of these are matrix multiplication. Some of these are simple, this is a ramp function. So they're doing lots of simple things, but lots and lots of them. And there's a lot of learnable parameters. So out of these, I don't know how many parameters there are in this, but there's perhaps couple of hundred layers. And within that, there are matrices that are, you can see some of these sizes, 320 by 27 by 27. So that each of those is a learnable parameter. There are tens of thousands of values, way distant now from my straight line where I could learn A and B. We've now got these tens of thousands of different A's, B's, C's, and so on to learn. And we feed it lots of images. And with some tools to make it not overfit, we end up that it turns out to be incredibly successful. So we can take that model and now apply it to a picture, and it can guess what it sees in the picture. And of course, we're now used to that. There's all kinds of image identification and self-driving cars are using this kind of thing, and face recognition and all of these. But in the end, all they're doing is that straight line fit that I did earlier, or a model fit, just loads of it in a very complicated way. Now, we can take a look inside and actually see the effect of those filters on the first level. So I just take the first level of that network, apply to that image, and turn them back into pictures. Here's what the effect of those filters are after detecting edges, corners. This is just the first round of filtering. I have no idea what these mean. When I had edge detection, I could tell you this finds edges. These filters are doing something that are picking out textures and features that it finds useful, but we don't have a word for them. It's almost like, if I was to try and describe what's in the picture, I would say, well, I can see some eyes and a nose and fur. That makes it more likely to be a dog. Well, those are abstractions. Eyes are an abstraction that we agree on. If you invented your own language, you'd have different words for them. We might not know what they are. And that's, I'll just take a couple minutes. I'll wrap up quickly. Sorry, I'm running out. And so, it's inventing its own abstractions and its own language. Let's go over this. I'll just end with the thing that is biggest today, and just be a couple of minutes on that, which is, all the headlines at the moment about artificial intelligence, and is generative AI has been the big step forward here. But in the end, these are just the same kind of thing. The generative adversarial networks are just learning things where you just pit one machine learning model against another to outwit each other as a way of getting the ground truth. I put this in because it happened to be on the news yesterday that it won an open photography competition, and then the winner admitted it was computer generated. That all you've done is describe a picture, and it did it. But the large language model, ChatGPT, in the end, they're just models. This idea that this is AI is still just an illusion, which is why I say the appearance, it's not the arrival, that all they do, and this is an earlier version of it, is to take a piece of, I'm just going to get the model and apply it to a sentence, is just a model to say what's the word that's most likely to come next. And here's our top probabilities that after this sentence, the most likely word at 27% is the word who. It just happens to be that now the model is so big, so rich, and it's captured so many features that when I apply it to a phrase like write a poem about fish and flies, and this is the GPT-3 model now, it's learned enough features that it's got short and long-term features. It knows about a rhyme, it knows about adverbs relating to verbs, it knows about beginning, middle, and end, but it doesn't understand anything more than my straight line did about driving. This is not intelligence. This is predicting what a good response would be to this. It just happens to be so good at it now that it passes for human. It does unfortunately have the problem that it is still a random probabilistic model that is doing guesses, just like my straight line does not prove where I am. This does not know things. It appears to know things, but I can ask it questions like this, and it's just done this. Let's see what he's got here. So I'm not the director of platforms. That's not my title. I am at Wolfram Research. I am involved in our cloud technology, but I don't actually drive that. 25 years experience, I probably said that somewhere, but I've been with the company 30 years now. It usually gets worse as you go down. So having studied at a local university in Australia, I've never been to Australia. I've never worked at Microsoft or the startup LiveOps. And so this is incredibly plausible. And I've seen examples where it even says, according to some database, and I looked up the database and it's a real database, but the fact I got from it was made up. So in the end, this is not knowledge or intelligence, it's just the appearance of it. But in the end, it's just models. And my end point, which hopefully I've kind of reiterated here, let's skip what we're doing with OpenAI at the moment, is that even though this modeling has become so much more powerful and so much more automated and more opaque at the same time, this is not a reason to let go of our roles, because actually the human choices in there are every bit and possibly more important than they were before. It's still modeling as a human process. And in the same way that driving is a human process still, even though I don't control the mixture of fuel in my car at all, I decide where the car goes and I decide what it does. And we need to be in that position with modeling.
Oh, that was fantastic.
Thank you.
So much.
I'm only 3 minutes over my private time.
Thank you very much. I just want to pass a register around. So if you put your name and details on there for me, there's a pen there to fill in forms. There's a few forms, so just keep going through and passing it to the next person, please. Meanwhile, what we're going to do is start the Q&A session. So we've got questions online, and Jeff, if you're okay, what we're going to do is have a question from our live audience and then a question from our online audience, and we'll keep swapping around until we reach 9 o'clock. So hopefully we'll get there. So if we start, if you've got a question in our live audience, do you want to put your hand up and ask your question, please? You let me know. Yes, would you like to have that? Sorry, what's your name?
Matthew.
Matthew, would you like to ask a question?
Yeah, sure. Where does something like, say, physics-informed models in the sort of realm of machine learning, it's something I've heard of, but I don't really know a whole lot about. Where does that fit in your sort of what you've kind of laid out here?
Yeah, so physics and informed models are still important. If you know the physics of it, one of the things I often I like saying a lot is that you've got classical modeling and machine learning, and my test is if you are understanding rich and data poor, then do physics-based modeling. If you are understanding poor and data rich, machine learning is your route to go. So if you happen to know that you've got a circuit, you know how circuits behave, don't try and have machine learning deal with that unless there's some black box in there you don't know how it behaves, in which case you're understanding poor. So you can do more with human created models if you understand things well in less data and in less time. So you should go there if you can. Another place that they're useful is to test whether your understanding is correct. So having a model for the theoretical behavior is actually the better way to drive out the anomalies. You've got a circuit, you know how it should behave, but it doesn't behave like that. Owning the modeling of what it should do tells you that there's something going on, and that's how you make discoveries. Machine learning, I know how it behaves. Now I can predict it. You don't discover anything that way, you only predict.
Thank you, Joel. Jeff, do you want to have the next question?
First question. Yeah, we've got a question that goes back right to the very beginning of your talk, which was the mesh presented, which I think was the spoon mesh, connected to the PDEs? And is that something that can just be done by the software?
Yes, yeah. So mesh generation, it turns out, is a complicated thing to do right, because it's easy enough in any kind of CAD package to draw something with a mesh, but actually to solve PDs, you need meshes that are quite evenly constructed, for example. And so taking an arbitrary shape, and there I started with the mesh, because that probably was a scan from a spoon or something that came in as a mesh. But if you take arbitrary shapes like a circle, you need to generate a mesh. You need to make sure that you've got meshes that capture features like the curvature of the edge, but are even in size. So we have some mesh generation capabilities. I can give it an arbitrary shape and say generate a mesh. I can do things like tell it how big or small the mesh size to make. I can look for degenerate mesh elements, which I forget what the definition of those are, but they're bad for PDE solving. And then the PDE is solved across the mesh. So yes, it is an integral part of the software to both generate and process the mesh.
Can I suggest we take the next question, because it was from the same person online?
Yes. Thank you.
There'll be some continuity.
There's a simple mesh generation, for example, of a disk.
Oh, lovely. Thank you.
I shall read the question as it stands, because I don't understand the question. It says, were the simulations presented for the airport data different models? So does this mean that we have fitted values for the distribution of models, or was it something else? I got a bit lost at that.
Yeah. So the model that I fitted was to find the right time series model. So a time series model like a distribution. So imagine you've got some data. I might say, oh, that looks like a normal distribution. Now, because I've got a normal distribution doesn't mean that I know what is going to come next. You know, if I say, let's take a simpler example. I know the heights are normally distributed around, I don't know, 5'10" for men, plus or minus, 6 inches or whatever. That might be a good predictor for what a room with 1,000 people in add up to in total, but it still doesn't tell me anything about the next person. So then when you do a simulation, you might say, well, let's make a person. And I might get one in 6 foot, I make another that's 5'4". It's the same model, but I'm getting a different case each time. And by doing it lots of times, you start getting the pattern. So that's basically what I'm doing. So it was one model, but every time I ran the simulation, I'm getting a different outcome. And then by taking the collection of outcomes, I can start learning what the patterns of the outcomes are. And that's the kind of essence of Monte Carlo.
Thank you, John. So could we have a question within this audience? Another one? We've got one.
There's one at the back. Yeah.
What's your name? Sorry.
Samir.
Samir. Yeah, ask away.
So you mentioned that you're working with OpenAI, and I was wondering how you incorporate Wolfram Language into OpenAI. So do you make it predict the Wolfram Language, or do you add on top of it?
Yes, well, so there's 3 main angles in this, and I'm just going to open this up now and do an example here. Let's do a question. I say I'm in ChatGPT here, and I've skipped the wait list on plugin, so I have the Wolfram plugin going on in the ChatGPT, and I'm going to ask it some question like, tell me about livestock populations in Turkey. Let's see if we can confuse it with the word Turkey. And hopefully, if things are all working correctly, I'll get a little essay out of ChatGPT. But what we've done is we've taught ChatGPT the kinds of things that we might know about and how to ask us. So this little used Wolfram has popped up. And in a moment, I'll show you what's behind the scenes here, but here's the essay that's coming back from ChatGPT. But the conversation that went on behind the scenes to achieve this is shown here, which is ChatGPT said, oh, call Wolfram Alpha and ask for livestock population in Turkey. It got this answer back, which you then use for the basis of the chat. So that's one route. Another route is, let's do something really simple, a bar chart of 1, 2, 3. Oops. In this case, it's going to figure out that what it needs to do is to write Wolfram language, hopefully. Use Wolfram. Let's let it think. So here it's written the Wolfram language code for generating a bar chart, which is actually now being executed on one of our servers. So we're actually running code that was written. Obviously, there's some security and safety issues there from our point of view, that we're running code that's been sent to us. But it's generated this bar chart. And we've got a loop set up where sometimes it'll hallucinate and say, use the super duper bar chart function. And we have to reply and say, no, that doesn't exist. And it tries again, and it can go through a couple of iterations while it writes code that then eventually successfully runs and gets the result back. You saw the other way around that I did from notebook, where from Wolfram language, I could call ChatGPT to do some essay writing. So we've got all kinds of interesting things where we can inject some modeled values into something to make an essay out of. And then there's this weird middle ground, which actually is what I'm most excited about, which is building models using the innate knowledge of, I just said knowledge, innate model of ChatGPT. So what this is called one-shot learning. What you do is you say, okay, I want to take some unstructured data like GP notes. And here's an example of that. And what I want to do is get out the patient's age, name, blood pressure, what they complained of, what medicine you gave them. And you say, here's an example of a GP record, and here's what I would want it to look like. And you write the bit of Wolfram language that says, name goes to this, blood pressure goes to this in units of millimeters of mercury, or whatever the units are. You give it 3 or 4 examples, maybe 100 examples, and then it extrapolates from that using the language model. You go, okay, I get it now. And you give it some unseen data, and it really magically pulls out structured information from unstructured data, which is now in a computable form for Wolfram language to be able to do modeling or data science or anything we want with. So that's, we work really hard on really mediocre tools for taking unstructured data and computing with them. And suddenly this has sort of solved a big chunk of that problem overnight. Yeah, I'm really excited about using those things.
Thank you. So, Brian, you got a question for us?
No, we've not got any more.
No more
questions.
I think that puts in there. Okay, anybody in the audience wants to ask questions?
Sure.
Yeah, of course. Yeah.
So do you send the examples every time? Every time a user asks something? So
In the ChatGPT interface. Yes, so at the moment, there's no caching going on. So every time ChatGPT is making a call to us and we're computing something dynamically to that call. I mean, there's a lot more to come in the space. These LLMs are so new that they're coming out all over the place at the moment. So we expect there to be choices of backends from these things and the ability to run them locally, so you don't have conversations going on. And ChatGPT's rules say they keep all the data you send them. So at the moment, for some people, that's a red flag that you can't put sensitive information in here because it's part of their training set the moment you do. But if you have it locally, that would not be the case.
I was just going to say, I loved your simulation of COVID because we saw that so many times on the news, and it's just I think there was an app that got all the information. I don't know if you read about that as well, so that they could generate, so the mobile phone would know I need somebody, and that would need somebody else. Yeah, I probably remember that. And that was amazing but it was also frightening. I kind of thought, well, it's just so proximity of one person to another, and it could just happen. And it's amazing how they could capture that. Yeah.
Although it's also, I think that was a good example of modeling failure in a way, because there was no model for how we captured it. So these kind of proximity pings of you walk past somebody in a supermarket, that counts the same as sitting down with a family member for 6 hours in the same room. And I think that's one of the reasons why at one point we got what was they called a pingdemic. The app saying you've been exposed when you had no measure of the level of exposure. And if they had something that said if you hold proximity for longer, or knowing about where they were in their infection cycle, those kinds of things, it might be more accurate. But in the end, I think it got disregarded because its predictions were too weak.
Yeah, and I think you touched on this, where if we need knowledge, we need human knowledge. So that would be medical knowledge, I guess, of really understanding what is actually COVID, how do we actually catch it, and what things make us catch it, like handshakes or sneezing, or as you say, touching. If you get close to someone, you're going to catch it. But it's kind of having the right baseline and having all that there before we. It's
actually another example of these post-analysis problems as well, because when something's happened for the first time, it's really hard to model.
Yeah.
Now we can look back and see what worked, what didn't. We can calibrate the predictions, and if we have another similar epidemic, we'll know much better what works and what doesn't. But yeah, modeling is very poor on first-time events. you've got no data and you've got no theory.
I really enjoyed your part about time series because my degree was in economics. I was predicting.
Oh, yeah, all kinds of time series in economics.
Yeah, and I was building models, but economic models. It's not as elaborate as what you're doing, but I find that you talked about how although we can say predict it's going to happen like this, but is it close to reality? And how close is it to reality?
Yeah.
And it's kind of, I remember doing that where we were trying to see, okay, we said this and this actually happened.
Yeah.
So how close did we get? And why did we get it wrong? Why did we get it right? So I find
And that's
that
another area
quite-
as you've studied that gets arbitrarily complicated, because there I just did a simple forward-looking problem. But if you've got feedback loops, if you've got staggered delay effects, then there's a whole world of modeling just in that one field.
I don't know if there's any more questions at all. Yeah. Oh, sorry, Brian.
That's all right.
Sorry, what's your name? Sorry.
John.
John, hi, John.
So just it's sort of following up slightly on probably what my colleague Matt asked. I just wonder a little bit if, and perhaps, Comfort can say it strikes me sometimes that these machine learning models are kind of the enemy of understanding at times. And I appreciate that if you say that physics informed models or models that are forced to obey certain rules or whatever, then yes, it can, as I think you said, it can show you where your theory is weak potentially, or other features that you haven't considered in your theory that would lead to better predictions and so on. But do you think there's a bit of danger that this might undermine a lot of science? Because if we have tools now that black boxes solve problems, then we don't need to understand the underlying moral science or the sort of fundamentals that go into it. So, whereas in the past we would have needed to understand the science in order to solve the problem. So, do you think that I'm just interested as your opinion on that, whether this is a it might almost be a sort of division of sort of science and technology, and that we don't need to understand things in the same way, or at least humans don't need to understand in the same way that we used to in the past, or not.
So I think I've got several different slices on that. One is I'm reminded of why my wife became a physicist, because she was told by her teacher when she was weighing up physics or engineering, is physicists ask why, engineers ask how. And so there's use in the world for how, and we need physicists to come along with the why. And it's almost a bit more like the way that you have, physicists break down into the experimentalists and the theoreticians. The experimentalists don't really have to understand why or how. Their job is to say, look at this interesting thing I did. And then the theoretician has to figure out the why. So I feel like machine learning can still be a part of that experimental side of saying, here's a model that predicts interesting things. We can test it. Oh, it works. Now, physicist, why is that? And you need to develop a theory to back that up. If you care about theory, we could be, the world managed without physics theories for 1,000 or 2 years before that came along. The other side of it, which is I think a more practical risk, is that it's going to be easy to abdicate responsibility and say, oh, well, I ran machine learning on it and I've got a prediction. And which is why one of the reasons why I want to labour the questions that still remain, that at least for the foreseeable future, you shouldn't ignore, although now it's going to be a lot easier to ignore. And I can solve my HR problem by making an AI that's been recruited and stuff and let it loose and not think about the fact that I've made some innate decisions there, some implied decisions by doing that. So I do worry slightly about people thinking that they don't need to think anymore. And particularly as this stuff gets better. Up to now, every time we destroy jobs has been a good thing for civilization. The hunter-gatherers complained the first time you put a fence around some cows and said, what am I going to do now? But in the end, we've always found higher things to do. And the reason we found higher things to do is because the thing that makes us unique compared to all the other animals is intelligence. So we've always allowed more time for intelligence by doing less washing dishes and farming for food and things like that. Now that we're actually challenging more intelligence-driven things that you don't need to do for yourself, hopefully civilization can rise and go, okay, great, we're free to think higher thoughts and not have to worry about little details like what decisions to make today and things like that. But it might be that whole sections of society say, well, I can't compete on those terms now. So just in the same way the bacteria are not losers because they can't think, They've gone for the different approach of multiplicity. Maybe without humans, go, well, I'm just going to take an alternative strategy to winning, like shooting people and stealing. I don't need to be clever for that. And you know, when intelligence becomes out of the reach of some, that may be a problem.
Brian, you had a question.
My question actually was very much related to the previous one. I think was that probably phrased much better than I could have done. But my worry is correlation and causation, and one doesn't mean the other.
Yes, and that's one of those human things you really have to think about. Even in classical modeling, you know,
yes,
you only have to read the newspaper to know how badly everyone gets that wrong. This went up and that went up, therefore we should do more of this.
Yeah. My worry at the moment is that everyone's jumping on this bandwagon and saying, you know, isn't this marvelous, without really knowing how it works. And from what you said, we may never know how it works. And that I see as a danger.
Yes, and it's also a big part of I do a whole hour on this topic sometimes, which is the you know, how you choose your data and what you can use from your data. So the cause and correlation is at the center of that, which is, are you trying to predict something or control it? And they're very different problems. So the example I always use is that if I look at sort of the facial hair of a person, I can tell whether they're an insurance risk driving. You know, it's not the strongest signal, but people with beards are more expensive, have more expensive accidents. Now, as a predictor, that's fine, but as a driver, it's no good at all, because of course it's a really correlated to the fact that men are worse insurance risks and men tend to have beards, or more men tend to have beards. And so the test is when you try and drive it by saying we can reduce traffic accidents by shaving everyone, then of course the signal vanishes, because you collected the data not in a controlled experiment way, but in an observational way. So you've got to know, how did you get the data and what are you trying to do with it? And cause and correlation really needs to be understood there. And even there, cause and correlation gets really complicated when you get properly into it.
I've got some more questions actually from our virtual audience.
Brilliant.
One says, this is more of a comment than a question, but it would be great to inspire some secondary stroke college students with this technology. I'm thinking of Sunak. Oh, Sunak's maths for 18. Sorry, it got split as two separate questions.
Okay, let me point you to my other project. We have a project that has been trying to answer a very simple question, which is, what should maths education look like if we assume computers exist? Because at the moment, our maths education is mostly focused on doing the computation, being the computer. And then you get some magic side effect where you kind of understand some higher ideas because you've been practicing long division and algebraic manipulation and so on. If we assume that in the real world, you're going to use a computer to do it, obviously you could take the lazy route and say, well, we don't need to know anything now, so let's just not know. But if we take the freeing you to think, then we could teach much more interesting kinds of maths, much higher maths, things like calculus, which we leave to the end because when you're doing the mechanics of it, you need to learn, first of all, your algebra, and then you have to learn your limits, and then you've got to learn something else, and you've got to have all this machinery before you can do an integral. If you don't have to do the integral, you just have to understand how to apply it and what it means. You could be doing that much younger. You could be doing calculus at 10. That's not unreasonable. And the idea of infinite limits is actually kind of a cool idea, I think, small kids can get. And things like, I don't know, fast Fourier transforms or something, and do signal processing there. Why leave that to university? But it's a hard slog because, you know, everyone's in the same position we are when we sat down and we would say things like, oh yes, well obviously we've got to teach standard deviation, and somebody would say why, and we'd think, well, and eventually we say, well, I learned it and I turned out okay. And so there's this gut reaction of you can't let go of this stuff because it's what made us who we are today, but actually the mechanics of the moment move on, and we should, yeah, I'm a big believer in embracing the new mechanics, which is computers for doing computing and the humans for doing computational thinking. This is the website that tells the story, and you can buy my boss's book, The Maths Fix, which tells the story.
There's another question here, which says, I've seen people use RNNs to create cellular automator. It says C linear. Could something like this be used for explainability? I wonder if there's been any research in this field.
Okay, I don't know the detailed answer to that, so, but to explain to everyone else, an RNN is a recurrent neural network. So the idea is that all of the neural network that I showed does simple calculations, passes them forward, and in theory they get higher and higher abstraction. So at some point, if I go back to this picture one that I had, and go to a level a lot later, say somewhere around level 20, then we're not seeing pictures anymore. We're seeing more abstract features like that dot there might represent dogginess or something, who knows. Now, the recurrent neural network is a mechanism for allowing it to feed backwards. So instead of just thinking instantaneously, here's a bit of information, pass it on and forget, you kind of form a bit of a loop. And you need those things for anything where you've got sequences. So language models for a long time were based around recurrent neural networks, because you would have a sequence of words and you would move the sequence forward, and you'd be thinking about all of the words that led to that moment, not just the word you're on at this present time. Now, serial automata, of course, work in sequences, so you can simulate any system arbitrarily closely with a sufficiently complex neural net. That's been proved. So you can certainly do that, but it's not necessarily going to be a more efficient way of doing it. So I wouldn't be surprised there's some research, but my gut reaction is I'm skeptical that it will do anything to shortcut. My super bosses, there's two Wolframs in my company. I work for Conrad Wolfram, who leads the European company here in Oxford. And the guy who's at the top of the company is his brother, Stephen Wolfram, who has this theory of computational irreducibility that says these complex systems like cellular automata, there simply is no shortcut. So in the way that we can shortcut repeated addition with multiplication, there's no shortcut for complex behavior when you've got a cellular automata. So you can approximate it, but because it's innately complex, you'll soon be wrong. And I'm kind of clinging to his theory on that to say that the RNNs won't really help anything. But I'm speaking beyond my expertise now.
I just wanted to ask for one more question before we wrap up. And I just wanted to check, Sheila, there you are. And the floor is open if anybody wants to carry on these conversations, I take it, or is it shut now?
I'm hoping that it will be open, but we must know the wrong. Because the person who's going to clear this room is going to open the bar.
Okay. So probably goes. Thank you for answering that question. Thanks, Sheila. Was there one last question anybody in the audience would like to ask? Okay, I think that's
okay. Thank you very much.
But thank you, John. You've been amazing. I've certainly enjoyed this talk, and it's great to have you at BCS Oxfordshire. It's been lovely to hear all your information. I think there's so much more to learn about what you've just said. I think it's kind of sown the seed really in my mind. And don't forget also this talk, you're happy for it to be recorded. Yep. This will go on our website, so it would enable people to review some of the information that's been talked about. So you can, if there's one bit you thought, I just want to investigate that, you can go back and review that video and have a look at that section. Well, thank you so much, John. I'm just going to go.